Okay, here we go. Second example on matching an equation to a graph. So here we have another graph. Here we have three equations. Which one of these three equations matches to this particular graph? So let's take a look. We're gonna do the same strategy. First strategy is to look at test points. So we're going to choose two test points such that when we plug them in, we'll either get true statements or false statements. And if we get a false statement, then we know that that point can't lie on the graph of that particular equation. So let's roll. What 2 points should we choose? So let's choose 1 point. Again, you can choose whatever points you want. You could choose this point if you wanted. Let's actually choose our points in a different color other than black, just so it's more distinguishable. Let's choose green. So wherever this line crosses, wherever this line clearly crosses an intersection of grid lines. So if I just trace these grid lines, and just tracing. I'm awful at this. I need to find out if I can use maybe some sort of ruler app or something. But in any case, these are the grid lines that I'm talking about in the background. I'm just sort of tracing them. There's really an infinite amount if you go in either direction. But if we follow along this line, we can see that here I'm not crossing a clear intersection of grid lines, but here I am. Right here I'm crossing a clear intersection of grid lines. Here I'm not. Here I'm crossing a clear intersection of grid lines. So that's how you should be choosing your points. Any point along some sort of clear intersection of grid lines where it's clear what the x and y values are, you could choose that point. I like choosing a y-intercept if it's clear what the y-intercept value is. Here, it's clear that when x is 0, y is 3. We have a height of 3 above the x-axis here. And let's choose this x-intercept as well. You don't necessarily have to choose this x-intercept. You could choose this particular point. You could choose this particular point of 2 and 2, or 4 and 1. But I'll just choose this x-intercept just because I want to. So here we have 6 and 0 as our second point. They're also usually nice and easy to calculate with if you have a 0 in there somewhere. Okay, so let's test the point. Let's test the point 0 and 3. Let's test that point. Where should we test it? Let's test it in this equation. And if when we plug in the x and corresponding y value of this particular point, if when we do that we get a true statement, then that represents a solution to this equation, and we are at least encouraged by that. So let's try. So here the equation is y equals negative a third times x plus 3. Now, what is the x value I'm plugging in? I'm plugging in an x value of 0, and the corresponding y value is 3. Now let's take a look at this. 3 is on the left-hand side. Negative 1/3 times 0 is just 0, so that's just 0. And then all we're left with is 3 on the right-hand side. Hey, the left side is equal to the right side. That's great. We are initially encouraged, but let's test another point, because it has to be that two points that we test, 2 points that we test must satisfy that equation. So if just one works, then it could also be a point that lies on some other line. So we need to test 2. All right, so let's test this second point of 6 and 0. So we rewrite the equation again. Y equals negative a third times x plus 3. What are the corresponding x and y values? Well, when x is 6, y is 0. So when x is 6, y is 0. Are we going to get a true statement here? 0 equals negative a third times 6, that's negative 2. And then plus 3, simplifying the right-hand side, we get 0 equals 1. That is not true. So we do not have a solution here. And what we can do is cross this out. This equation does not match this particular graph. Right? It matched it for this particular point, so if we were to graph this equation, then it would go through this point. And I'll tell you what it looks like right now. We would go down by 1 and to the right by 3, and then down by 1 and to the right by 3, because that's its slope, and then so on in reverse. And this is what the graph of that equation looks like. So they are clearly different lines. They are very similar, but and one of the similarities is that they both have the same y-intercept. But just because they share one point, just because they share this one point here, doesn't necessarily mean that they're going to have identical equations, right? In fact, it's not that it doesn't necessarily mean it. It doesn't mean that at all, because this has a different x-intercept clearly than this blue line. So this this red line, which would be the line of all of the solutions for this first equation, does not quite work. Let's try another equation, see if it works. So for this second equation, in this second row, we have y equals negative x plus 6. So let's see if this works here. And by the way, I actually want to change this up a bit. So I'm not actually going to change the relation. So the relation is going to be the same here. But I'm just going to write it differently because I think it's worthwhile to show you an example of plugging in test points for some equation that is organized differently and it's not necessarily solved for y. And in fact, I'll do that here as well. So let's do 1/2 x plus y equals 3. So again, I'm not changing the relationships here. But let's actually change this even more to y and 6. So again, this is the same relation as what I had written there previously. It's just that I'm representing it differently because I want you to see an example of applying test points where it's not in the form y equals. All right, so where was I? We're plugging in a test point of 0 and 3 into this particular equation. So when x is, let's get my black ink back. So x plus y equals 6 is the equation. Let's plug in the particular corresponding values of when x is 0, y is 3. Then we get 3 equals 6, and that is not true. So we can immediately just reject this, right? This point does not work as a solution when we plug in the corresponding x and y values, right? We get this false statement, and so we reject that equation. By process of elimination, you can guess that this last one is it, but let's try it more systematically here. So here we have x plus 2 times y equals 6. And here, when x is 0, y is 3. So let's do the calculation here. 0 is 0. 2 times 3 is 6. 6 is definitely equal to 6. The left side is equal to the right side. We get a true statement. And let's try this other point. So we are initially encouraged, but we were initially encouraged with this top row. So let's just double check. Let's just double check here by plugging in some other solution. So the equation states that our x value plus double our y value should be equal to 6. And so will this corresponding x and y value be a solution to that equation? Well, when x is 6, y is 0, so says that line. And 2 times 0 is 0, so we have 6 is equal to 6. Hey, there you go. The left side is equal to the right side. Again, we are doubly encouraged and, in fact, confident and sure that this is our match. In this particular case, the test point method is really the best method to use, particularly because I performed this last minute change here, right? I didn't write all of these equations in slope-intercept form, or in other words, I didn't write all of these equations as being solved for y, right? So these equations aren't necessarily written in terms of y equals mx plus b, where the slope is clear at the outset and the y-intercept is clear at the outset. But if I were to solve this for y, which I will do quickly just to demonstrate for you, by the way, if you understood how to use these test points, I'm happy. That's great. But I'm going to go a little bit further. So again, if you get confused by me going a little bit further, shut the video off and then try some examples, because I don't want to make you feel like you're just starting to get something and then start to throw you off. So I'm just going to go a little bit further. So just a warning for those of you who might want to just jump to the questions first. So I'll show you how to use the y-intercept and slope method. So my equation is x plus 2y equals 6. I want to put this into what's called slope-intercept form. So I'll write that. This is called slope-intercept form. And to put it into slope-intercept form, all I have to do is solve for y. So let's do that by getting rid of the x. So I subtract x from both sides. Again, this is an additional method. You don't necessarily need to be doing this right now. You should know how to solve for y, though, algebraically. Right? We're just trying to isolate this variable here. And so how else could we isolate this variable? Actually, well, we know that y is being multiplied by 2, and to get rid of that multiplication, we just divide by 2. And we divide the whole right-hand side by 2. And then we get more simply y equals negative x plus 6 over 2. Let's split this fraction up. So negative x over 2 plus 6 over 2. When we do that, we can see that we have a constant of just 3, right? 6 over 2 is just 3. And negative x over 2, I'm just going to write the coefficient out in front. So I'm just going to write negative x over 2 as negative 1 over 2 x. So this is the equation in slope-intercept form. Why is it interesting to put this into slope-intercept form? Because here you can spot, I'll do this in blue, here you can spot that the coefficient in front of your x is your slope. And another way to state that is that it's your rise over run. So how far up you go versus how far across you go. So negative 1 over 2. And again, and I'll take the sign in front of it. It's positive 3. Here we can see that the y-intercept, or the b value, is positive 3. So this is helpful for us because we can compare it with the information from the graph. So if we look at this graph, we can notice, let's call this point A, and we can call this point B. How far do we have to go down to get to the same height as point B? Well, that would be a rise of negative 1, 2, 3. Why negative 3? Because we're going down. So if you're going from A to B and you end up having to go in the downward direction, in math we label that with a negative sign. So we're going down by 3. And then how far across do we have to go? Well, 1, 2, 3, 4, 5, 6. 6 units across. So we have a run of 6. So we have a rise of negative 3 and a run of 6. So for the graph, oops, I'm going into the other example there. So for the graph, we see we clearly have a rise of negative 3 and a run of 6. And you might initially say, hey, that doesn't match the equation that we were working with, right? You might initially say, hey, these are two different slopes. But no, they are not. This is one of many reasons why it's good to be able to simplify your fractions. Negative 3 over 6, divide the top by 3, divide the bottom by 3, you get negative 1 over 2. Or negative 3/6 is really just negative 1/2. So the slope matches. So we have a match between the slope of the graph and the slope of the equation. Right? We have a match. But again, it's not just the slopes that have to match, it's the y-intercepts. So what is the y-intercept? Well, here is where the graph crosses the y-axis at a y value of 3. So our b value from the graph is 3, and we have another match. If both the slope and the y-intercept of a graph match with the m value and b value of a linear equation, then the equation and the graph match. This will always be true. If you have the slope of some line and it matches with the m value of your equation, and you have the y-intercept of some line and that matches with the b value of some equation, then that particular equation matches with that particular graph. And any particular point on that line would represent a solution for that particular equation. So hopefully that makes a bit of sense. Again, if you understood how to do the test points, that's really good enough for now. But I do encourage you to practice looking more into finding slope and y-intercepts of graphs and using that as a method to match equations to graphs as well.